stoichiometry. Alright, the first one is balancing chemical equations. So when you actually have a reaction, you mixing some chemicals together, they react, they produce something new. That's the physical reaction that we're talking about. But when we try to write it down on paper to represent it in the way that we can think about it and do calculations, that's called a chemical equation. And I think that makes sense, an equation like in math. And so it represents the physical reality. And chemical equations have this always a standard way where we got an arrow that separates on the left side the reactants and on the right side the products. So the reactants are simply those things that you're mixing together actually. Whereas the products are those things that are being produced when the reactants react with each other. Right, and so for example here, methane, CH4, reacts with oxygen, O2. That's a gas. This is also a gas. We use a plus sign between them, just meaning, hey, I've got a methane molecule, I've got an oxygen molecule, and they're going to come together and react. So we're putting them both in the same beaker or in the same vessel at the same time. So we're adding them together in that sense. The arrow, this means they're going to become, after they react, CO2 in this example, and water. That's a gas. This could be a gas or a liquid, I suppose. And so this is just burning natural gas, methane, in your furnace or your stove, something like that. And this would be the chemical equation representing that. All right. Notice that when the reaction occurs, the reactants will no longer be around, and the products, which weren't around initially, come to be around or come into existence. We're not creating or destroying matter. We're just shuffling these atoms around, what's connected to what, so that the reactants are no longer and the products appear. Now in this example here, we do not have a balanced equation yet. That is to say, our conservation of mass has not been obeyed. I mean, if you look at it, we've got 4 total hydrogen atoms, and yet over here on the right side we only have 2 hydrogen atoms. So it's like 2 of them have just disappeared. We know that can't really happen. And so the process of balancing these is using the idea of conservation of mass so that that's obeyed correctly. In other words, if I have 4 hydrogen atoms on the left, I better get 4 hydrogens on the right as well. If I've got 1 carbon on the left, I better have 1 carbon on the right, etc., etc. All right, and so here's one rule. You can only change the coefficients, that is to say the numbers out in front. All right, so for example, if we look at this, I see 1 carbon here on the left, 1 carbon on the right, so that's okay. I've got 4 hydrogens here on the left, only 2 on the right. So I need to increase this. I cannot just take this 2 and change it to a 4 because I wouldn't have water anymore. H2O is water, not H4O. H4O is some nonsensical thing that doesn't even exist. Right? So you are not allowed to change the subscript. You're not allowed to change the molecule. In other words, we are allowed to change how many are there though. All right? So if I want 4 hydrogens, one way to do that is to put a 2 in front. That's called the coefficient, in front of the molecule. So instead of just this implied 1, now we actually have a 2 here. See, if I put a 2 there, now I've got 2 whole water molecules, and that's a grand total of 4 hydrogens, which is the same thing over on the left, which is a 4. If you look back up here, 2 oxygens, ooh, and a 3rd oxygen. Right? So that doesn't balance. But let's just keep working actually here on the ones that we're changing the coefficients. I put a 2 in front of the water, so now I actually have 2 oxygens and 2 over here. That's a grand total of 4, whereas on the left side I only had 2, so I put a 2 out in front of that. Now I've got 4 there. Once I think I've got it all balanced, always go back and check just to make sure. So 1 carbon, 1 carbon, that looks good. 4 hydrogens, 4 hydrogens, looks good. 4 oxygens, 2 here, 2 here, that's a grand total of 4. Now I have a balanced equation. Notice that the 1s you don't write. Just like in algebra, you don't usually write 1x, but you would write 2x or 3x. But if it's just 1x, we leave it off. And it's the same rule here in chemistry. If it's just a 1, leave it off, don't write the 1. But if it's greater than that, go ahead and write it. Alright, so this is my balanced equation, and it tells me that relationship then between how many of each molecule react. So in other words, for every 1 methane, I'm going to need 2 oxygen molecules. I'm going to produce 1 molecule of carbon dioxide and 2 molecules of water. That's balance. Conservation of mass is being obeyed. So let's take a look. Example 4.1 in the textbook. Let me pull that up here. Example 4.1. Here we go. Oops, there it is. It says balance or write a balanced equation for the reaction of nitrogen, which is N2, and oxygen to form dinitrogen pentoxide. Alright, so nitrogen plus oxygen give me dinitrogen pentoxide. Okay, so what we need to do, let me go to my scrap paper here, is first just write this out. Okay, so nitrogen is N2, of course, and it's reacting with oxygen, which is O2. It says it produces dinitrogen pentoxide, N2O5. Again, you got to be able to write the formulas from the names. Alright, if I look at this, on the left I've got 2 nitrogens, and on the right I've got 2 nitrogens, so that's good. 2 oxygens and 5 oxygens. So I've got more here on the right. I've got to increase this. But notice I've got this problem. This is an even number and this is an odd number. If I put a 2, that would be a 4 oxygens. If I put a 3 out here, it'd be 6 oxygens. How am I going to get 5? Well, there's 2 ways to think about that. The way I like to think about it, if I've got that problem, just multiply everything through by 2. That's the easiest way. So in other words, let me actually go to red. If I put a 2 here, and this is 1 times 2, so I'm going to 2 here and a 2 here. I say because I've done the same thing all the way throughout, I haven't affected anything else by doing that. But it should make it easier to balance now, because here I've got 4, now I've got 10. Alright, 10 oxygens. See, now they're both even, and I can balance this easier. So 10 oxygens, I can make this 10 oxygens by changing this 2, so erase that 2, and let's change it to a 5. Right? Now I've got 5 times 2, that's 10 oxygens. Over here is also 10 oxygens. That works. Let's go back and check the nitrogens though, because I was messing with things, right? 4 nitrogens, 4 nitrogens. Oh, it works perfectly. So there is my balanced equation for that. 2 N2s plus 5 O2s to give you 2 dinitrogen pentoxides. Alright, so often if you get that even odd thing, just multiply through by 2 and that'll clarify it pretty quickly. Alright, back to the notes. Another rule here is that the coefficients should be the smallest whole number ratios possible. Right. However, they said fractions can be useful as well. Alright, so for example, if I go back to my scrap there, 2, 5, and 2. Those are the smallest whole number ratios. Now, I might have come up with something like looks like this. I might have come up with, I don't know, 4 N2s and 10 O2s to give me 4 N2O5s. Now that's also balanced. If you look at this, I've got 8 nitrogens and 8 nitrogens. I've got 20 oxygens and 4 times 5, 20 oxygens. So it is balanced. However, 4 to 10 to 4, I recognize that all of those are divisible by 2. And if I went through and divided by 2, I would get what I originally had, a 2, 5, and a 2. Alright, so while this is balanced, it's technically wrong. You want to go to this one, which has the lowest whole number ratios. Now the other thing that they were talking about with fractions here in the book is sometimes it's useful to use them. So let's look at this. C2H6 plus O2 to give me H2O and CO2. And we've got the 7 halves here. Let me demonstrate where that comes from. Let's go back to my scrap paper and let me rewrite this. I've got C2H6 and it's reacting with oxygen to form CO2 and water. This is, by the way, called a combustion reaction, reacting an organic fuel, one that has carbons and hydrogens and such, with oxygen. Turns out you always get the same product, carbon dioxide and water, and that's what we're seeing here. Alright, so now if I want to try to balance this, I've got 2 carbons, I could put a 2 out in front right here, now I've got 2 carbons. 6 hydrogens, I've got 2 here, nowhere else, so if I put a 3 out here, now I've got 6 hydrogens. How about the oxygens? I've got 2 on the left and, let's see, 4 here plus 3, that's 7. Alright, so I need a grand total of 7 on the left, but it comes as pairs, so I can get 2, 4, 6, 8. I'm not going to get 7. Right. One way to do that, multiply through by 2, like I told you before. Alright. Another way, and so I could do that and it would work just like I did above, so I won't show you that. But another way is to recognize because these are paired, you could actually put a 7 halves out here. That way, 7 halves times 2 is 7. Okay, so I've got 7 oxygens on the right, 7 on the left, and technically that's balanced, except they're not whole numbers. What do I need to do? I need to multiply through by 2 to clear that off. Oh, you see, I'm going to end up multiplying through by 2 anyway. All right, what if I do that? Let's see, I would get a 2 out in here. This would now become a 7. This is now a 4, and this is now a 6. So I got a 2, 7, 4, 6, and that's the lowest whole number ratio. Now again, maybe an easier way that I prefer is to not necessarily use fractions, is to just multiply through by 2 initially. So let me show you how that would work. Go back here. I saw 2 carbons, so I put a 2 out here. I had 6 hydrogens, so I put a 3 out here, so 6. And then I found that thing where I had 7 total oxygens on the right, but an even number, there's 2 on the left. So I said, all right, odd even thing, multiply through by 2. So 1 times 2 is 2. Here is a 2. This is now a 4, and this is now a 6. Now, I haven't changed any carbons or the hydrogens because I did the same thing to everything, so those are still balanced. But now look at the oxygens. I've got 8 plus 6. 8 plus 6 is 14 total. On the left here, I could get a 14 by putting a 7 out in front there. Now I've got 14, and I'm done. Okay, so if you go back and check it again, 4 carbons and 4 carbons, 12 hydrogens, 6 times 2, that's 12 hydrogens, and oxygen's 14, and as I just showed you, 14. So you know what, it works both ways. If you like the fractions, that's fine. If you don't, that's fine too. Okay. And let's see, that's the same result that we got before. Phase symbols. Phase symbols are often included in a balanced chemical equation to show what state the reactants and the products are in. By state, I mean, are they gases, liquids, solids? Are they dissolved in water? All right. You'll see, those are the main ones that you'll see. And so, for example, here, sodium plus water to give you sodium hydroxide and hydrogen. The phase symbols are put in parentheses after each thing. And so S, that's for solid sodium, so it's probably metal. L for liquid, so that you put the sodium solid into a liquid water, put it into a beaker. You get sodium hydroxide, AQ. Well, this is an ionic compound, but in water it dissolves just fine. And so AQ means aqueous. It would have been a solid except it's dissolved in water, so we put AQ. And actually AQ show up a lot because that's very often how we do our chemical reactions. And then G here for gas, and so this gas must have come bubbling out of the solution when the reaction occurred. Another symbol you might see, it's not a phase symbol, but you'll see it sometimes as a triangle. A triangle in chemistry just means heat. And so for example, calcium carbonate, which is a solid. Hey, there's no other reactants. I'm not putting anything else in the beaker with this. However, if I heat it, put that over the reaction arrow, meaning I'm going to apply heat to this, I get calcium oxide and carbon dioxide form. This is the solid that gas is given off. All right, so this just goes by itself, but it requires some heat in order to do it. All right. Now that we have this idea of what a balanced chemical reaction looks like and what the phases are, the phase symbols, we can turn our attention to ionic reactions in water. Actually, you could do them in other solvents as well, but water's exclusively what we'll use here in Gen Chem. All right. Ionic reactions. So these are reactions involving ions, ionic solids in particular. We can break these in 3 different forms, and each one is useful in its own sense. The first form is the molecular, and that's kind of what we've been doing so far. So here's an example. Calcium chloride is reacting with, and it's aqueous, is reacting with silver nitrate. It's also aqueous. So we have 2 solutions, both of them in water, and essentially we pour them together, and so it's all in the same beaker. We're adding them together. They both were dissolved in water. They were both aqueous. The reaction occurs and we get calcium nitrate, which is also aqueous, and silver chloride, which is solid. So when we pour them together, they react and we actually see solid silver chloride start to form. It's not soluble. It's like trying to put sand into water. It's not going to dissolve. All right, and so all of a sudden you get the solid appearing, which makes that look very cloudy. Before you could see through the liquid, it was clear. That means everything was dissolved. You get that cloudiness of the liquid, that's a solid forming. And if you sit there if you let the beaker sit there for a while, that solid will settle down, it'll fall to the bottom of the beaker, and you get this little layer of solid on the bottom of the beaker. When that happens, by the way, we call it a precipitate. A precipitate, just like precipitation, snow, rain falling from the sky, same idea. But here we have a solid falling out of liquid and collecting at the bottom of the beaker. So a precipitate is a solid that came out of solution that wasn't there before. Alright, now in this equation we have balanced it already, so we have a 2 here and a 2 here, and so conservation of mass, we've written that correctly. The second way we could represent that is a complete ionic equation. This shows what it really would look like in that solution. You see, when I have this calcium chloride and it's dissolved, ionic compounds, this is important, ionic compounds when they dissolve in water separate. They separate into the positive part and the negative part. They don't stay together. You put them in water, water has a great ability to take them apart and stabilize them as ions. So, calcium chloride again. I recognize that as being a Ca2 plus and a Cl with a 1 minus. We have 2 of them. So if that all comes apart when I put it in water, I'm actually getting a Ca2 plus and 2 chlorides, Cl minuses. Right, so this becomes those 2. That's what it really looks like in that first beaker. In the second beaker, we said we had silver nitrate, and it was aqueous, which means it's dissolved. And so I really have an Ag plus and an NO3 minus. You got to remember all those molecular ions, right? So an Ag plus and an NO3 minus. I forgot to put my minus sign on that. Let me go ahead and add that right now. That's an NO3 with a minus charge. There we go. And because there was 2 of them, so I got a 2 in front of each one of those as well. Okay, and all of these ions are technically aqueous because they're still dissolved in the water. And so the molecular equation showed it this way, which is maybe a little neater, easier to see. The complete ionic equation shows how it really exists. All those ions are separate and they're all just swimming around in the solution. Now when they react, what happens? They swap partners, if you will. The positive and the negative, they swap what they were connected to before. So before we had calcium connected to chloride. Positive calcium, 2 plus, chloride, 1 minus. Over here, silver plus nitrate, NO3 minus. And so if we swap them, the calcium from this one, the positive, would attach to the negative nitrate over here. And the positive silver would attach to the negative chloride over there. And so that's exactly what happens. We've got calcium attached to the nitrate, silver attached to the chloride. All right, so we're swapping partners. In solution for the complete ionic equation, what's happening? Here's the calcium, here's the nitrate, and again, I am missing my minus sign. Let's put that in right now. There we go. And silver chloride. Now notice the difference here. Nitrate is a soluble ion. Calcium, where am I looking? Oh yeah, right there. Nitrate soluble. Calcium also soluble. But silver and chloride, when they come together to give you silver 1 chloride, that's actually an insoluble compound. In other words, it's kind of like, again, sand in water. It doesn't dissolve. Okay, you can stir it all day long. It's not going to dissolve. It actually stays together. So it's a solid. All right, so the complete ionic equation, if it's a soluble ionic solid, the complete ionic equation shows them as ions. If it's an insoluble one, so they don't separate into the ions, they stay together, like silver chloride over here, well, then it stays together in this form as well. So there we go. There's my complete ionic equation, and it shows all the ions except for the ones that are insoluble. Those are not ions. Now if you look at this, I've got nitrate here, 2 of them on the right side, and on the left side I've got 2 nitrates. Same thing with the calciums. I've got a calcium 2 plus and another calcium 2 plus. Technically, the before and the after, they've not changed. They're just out there in solution at the beginning. They're still out there in solution at the end. Those are called spectator ions because nothing's changing on them. It's like they're just hanging out watching. Right? But some things have changed. The chloride and the silver ion beforehand were dissolved and they are out there, but then after they reacted, they stuck together and formed this insoluble silver chloride, and so those have changed. Before they were independent, separate. Now they're stuck together as a solid that's not soluble. So that's what's really changing, and brings us to the third type of equation that we could write this as the net ionic. The net ionic says, hey, The spectators, there's nothing changing about them. Don't include them. They're boring. Only include the things that are changing, all right, which were the 2 silvers and the 2 chlorides. They came together to give me 2 silver chlorides as a solid. That would be my net ionic equation. So what's really important here is obviously solubility, whether something dissolves and whether it doesn't. And how do you predict that? We'll get to that in the next section.